Okay, so today we're going to be talking about experimental and theoretical probability. So let's go ahead and fill in these blanks right up here. So first we have experimental probability. So if you think about experimental, that's like doing an experiment. So if you think about if you're going to do an experiment, you're going to be able to see what actually happens in the experiment. You're going to be able to see the results. So whenever we are talking about experimental probability, that is what does happen. You see what happens if you flip a coin, if you roll a dice. You're actually seeing what happens, what really does happen when you perform an experiment. So experimental probability is what actually happens. So what you would see happen in an experiment. Now, with theoretical probability, so if you think about, if you've ever heard somebody say the phrase like, in theory, this is what should happen. So not necessarily what really does happen, but if you've ever heard somebody say, in theory, this is what should happen. That's what we're kind of talking about right here in theoretical probability. So it is what should happen, but we know if you're thinking about, okay, I'm gonna flip a coin. Okay, I'm gonna flip a coin, and it should land on heads about half the time, and it should land on tails half the time. And that's what should happen. But in a minute, we're going to get ready to perform the experiment, and we'll be able to see if, yes, that's what should happen, but is that really what happens when you flip a coin, a certain number of times? So theoretical probability is what should happen, what you would think happens in an experiment without performing the experiment. So what you would think would happen in an experiment. So before you perform the experiment, you could think about what should happen. That is going to be the theoretical probability, but then if you actually do perform the experiment, then that would be us talking about experimental probability. So let's go ahead and look at some things. So we can use theoretical probability to make predictions about an experiment. So how many times can we expect to land on heads if a penny is flipped 20 times? So I already did this, so let's just kind of hide that for a second. So if we go back to this, how many times can we expect, theoretically, how many times can we expect to land on heads if the coin is flipped 20 times? So thinking about a penny, it's got heads and tails. If you flip the coin 20 times, we would think that about half the time it would land on heads, right? And about half the time it would land on tails. So before we perform the experiment, theoretically, about 10 times, half the times it should land on heads. And the other half of the times it should land on tails. We know that's what should happen, but we don't know that that's always going to happen perfectly. So looking at what I did here, so I flipped the penny 20 times before I started this video, and I used tallies to record how many times it landed on heads and how many times it landed on tails. So by flipping it 20 times, I got 9 heads and 11 tails. So almost half and half, but not exactly 10 and 10. So theoretically, yes, it should land on heads 10 times, but that didn't really happen. Now, if you flip the coin maybe 100 times, it'll probably be closer to 50-50. If you flip the coin 10,000 times, a ton of times, then it would probably get closer and closer to 50-50. But by just flipping it 20 times, we've got 9 and 11. So what is the probability of flipping a penny and landing on heads during the 20 trials? So now we're talking about experimental probability. What really happened was it landed on heads 9 times out of 20. So we are writing 9 out of 20. That's how many times it landed on heads. And that is experimental probability. because we actually performed the experiment. Okay, so down here we're going to classify each scenario as experimental or theoretical. So number 1, Jordan took 64 shots during basketball practice. He made 40 of the shots he took. He determined the probability of making his next shot is 5/8. So when we're trying to determine experimental or theoretical, we need to think about, did somebody actually perform an experiment, or are they just thinking about what would happen? Well, it says he took 64 shots and he made 40. So that's an actual experiment that went on. He actually took 64 shots, and so he performed the experiment. So we are considering that experimental probability. Okay, number 2. A spinner has 5 equally likely outcomes labeled 1 through 5. Becky determined the probability of spinning a 4 is 20%. Okay, so think about a spinner that has 5 spaces labeled 1 through 5. Theoretically, we should land on each number about 1/5 of the time. So 1/5 of the time is 20%. So before she even spins the spinner, she's saying, well, theoretically, it should land on a 4 1/5 of the time, or 20% of the time. And so without even performing the experiment, that's what she is thinking will happen. So that is theoretical probability because it doesn't say anywhere that she actually performed the experiment. Okay, number 3. A bag of Skittles contains 4 yellow, 8 red, 9 purple, 6 orange, and 3 green Skittles. Robert determined the probability of choosing a yellow or a red Skittle next is 2/5. Okay, so does it say that he actually picked out Skittles one by one and actually found the probability? No. What he is saying is, theoretically, if I choose a yellow or a red, theoretically that should be 2/5, because let's actually go through and do this. So there's 4 yellow and 8 red. 8 plus 4 is 12. So let's add up the total. So we've got 4 plus 8 plus 9 plus 6 plus 3. If we add them all together, we get 30. Okay, so 12/30, we can simplify that down. Let's simplify by 2 first. So that would be 6/15. And then if we simplify by 3, that'll give us 2/5. So what he's saying, he did not perform the experiment, but he's saying theoretically, so there's 12 yellow or red out of 30 total. So theoretically, there should be a 2/5 or a 2/5 probability that you pick a yellow or red Skittle next. But they haven't actually performed the experiment, so we're labeling that theoretical. Okay, so you have to look at, what is the wording saying? Is it saying that we are actually performing the experiment or not? Okay, so let's do a couple of practice problems over here. So number 4, Cheryl randomly surveyed students at her school to find out what transportation method they used to get to school. The results of the survey are shown below. So 30 students ride the bus, 3 students walk, 9 students ride their bike, and 18 students take their car. So what is the probability that the next student Cheryl surveys will get to school by walking? And it says, give the probability as a fraction. Okay, so we want to, looking at the table here, what is the probability that the student goes to school by walking? So there are 3 students that get to school by walking, and then we need to figure out how many total students there are. So we're gonna add up all of these categories. So we've got 30 plus 3 plus 9 plus 18. So there are 60 students total that she surveyed, and it says how many get to school by walking. So 3 walk to school out of 60. Okay, so if this is the probability that they're looking for as a fraction, this is a fraction, we always, last step, want to make sure that we are simplifying our fraction. So before we can leave this as our final answer, we need to simplify. So we can simplify the top and the bottom by 3. 3 divided by 3 is 1. 60 divided by 3 is 20. So they performed the experiment, so it is experimental probability, And there is a 1/20 chance that the next student she surveys will get to school by walking. Okay? Last one. Each of the letters from the word spring break are put in a bag without looking. What is the probability of drawing the letter R? Give the answer as a fraction, as a decimal, and as a percent. Okay, so if you were to cut up all of the letters from the word spring break, put them in a bag, what is the probability of drawing the letter R? So we need to count up how many letter R's there are. So here's one, and here's another. So there are 2 letters that are R, and then we need to count up the total number of letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 total letters. So the probability of drawing the letter R is 2/11. Now, again, you want to think about, can this be simplified? That cannot be simplified any further. So that is our fraction answer. That's our final fraction answer. So in order to make this as a decimal, I don't know if you remember, but in order to make this as a decimal, we're going to divide top by bottom. So 2 divided by 11 is 0.18 repeating. So we'll just round it off to 0.18, 18 hundredths. So that is equal to 18 hundredths as a decimal. All right, and then lastly, in order to make a decimal into a percent, so we want to take this decimal and we want to move it 2 places to the right. Or in other words, multiply by 100. So if you multiply by 100, then we get about 18.18%, but we'll just leave it as 18%. So if you ever are asked to change your fraction into a decimal or your decimal into a percent, that is how we are going to do that.